Hi, everyone. Welcome to discussion section. Let's do some homework problems. Problem. Homework problem and let's do some homework.
I think your mic is cutting a little bit in and out.
You guys have been struggling on. Okay, I can plug in my cord. Is that necessary? Let's do that. Can you hear me? Oh, okay. Let me go plug in my Ethernet cord. I'll be right back.
All right.
Hello, I'm back. Can you hear me?
Yeah, that's much better.
Okay. All right. So let me get the first problem up. Is my screen not being? Sorry about this, everyone. Some technical difficulties. All right. So you can see my screen, correct?
Yep.
Okay. So I am trying to get to the next page. Let me do continuous scroll. There we go. I should be able to. Okay. So let's start with it doesn't really matter. We could do several of them. How about this one? There's been a lot of questions about on Piazza about this one. So here's the problem. Take a couple minutes and look at that, and then we'll do it. I'll be right back. I'm just going to plug my Ethernet cable into my computer. But in the meantime, think a little bit about this problem. Okay, so part A, what is the probability that in 5 holes the golfer gets at least 2 holes in one? By the way, there was a question on Piazza about can a golfer get a hole in one and a par at the same time? And the answer is no. So in golf, you can get a hole in one, and that is totally disjoint from getting a par, and that's disjoint from getting any other result. You can only get one score. So it says, what is the probability that in 5 holes the golfer gets at least 2 holes in one? So what we have is these 5 scores, like these 5 holes, 1, 2, 3, 4, 5, and we want to know what's the probability that the golfer gets at least 2 holes in one. So first we can figure out what the size of the sample space is. So there are 3 options. Actually, that's not a good way to do this one. If we do it, the problem is that the events aren't all equally likely. So if you just try to add up the events in the usual way, you might get into trouble. So instead, we're just going to use the complement rule. So let me start over. So we still have these 5 slots. Let A be the event that the golfer gets at least 2 holes in one, and the complement of 2 holes in one is 0 or 1 holes in one. So we're going to compute the probability of A complement, and that's going to be a little bit easier. So this is the probability, this was holes in one. This is the probability of 0 holes in one, or 1 hole in one. And those are disjoint events, hole in one. So since they're disjoint events, and this is an OR, this OR is really like a union, and these are two sets. These are 2 events. The event that there are 0 holes in one, and the event that there's 1 hole in one. And so the probability of the union for disjoint events is just the sum of the probabilities. So this is equal to the probability of 0 holes in one plus the probability of 1 hole in one. Okay, so this looks a little bit easier to deal with. We just have to compute the probability of 0 holes in one and 1 hole in one. So let's start with the first probability. There are 5 slots, and what we're saying is that or 5 holes, and in each one they're not getting a hole in one. The probability of a hole in one is 2/3. So each of these events is independent. And there are 5 of them. So the probability that they don't get a hole in one on all 5 is 2/3 to the 5th. So this is going to be 2/3 to the 5th. Are there any questions about that part? We're not quite done, but almost. Okay, then the other part is that they get 1 hole in one. So now there are 5 different spots here. So there are 5 different ways that they could get that we could choose that 1 hole in one. And then for each of those, well, there are 4 holes where they didn't get a hole in one. So again, the outcomes on holes are independent. So this is 2/3 to the 4th. And then there's that 1 hole where they did get the hole in one, and that happens with probability 1/3. So so the probability of 1 hole in one is 5 times 2/3 to the 4th times 1/3. So in total, the probability of A complement, just to summarize, it's 2/3 to the 5th plus 5 times 2/3 to the 4th times 1/3. So now we use the complement rule to get the probability of the event of interest. So the event of interest is that the golfer gets at least 2 holes in 1. We just computed the probability that they got less than 2 holes in 1. And so the probability of A is just 1 minus the probability of A complement. Are there any questions about part A?
Why is it that it's 5 times 2 to the 3rd to the 4th or whatever?
So in computing the probability of 1 hole in 1, what we've really done is split this up into 5 disjoint events. So I'll just write it up here. The probability of 1 hole in 1, oops, there's a message in the chat. Yes.
Oh, is it because any of the 5 holes could be the 1 hole in 1?
Yes, that's exactly right. So the 5 comes from the fact that we don't know which hole it was they got the hole in 1. And then after, for each one of those possibilities, so let's say that they got the hole in 1 on the first hole, then we know they didn't get a hole in 1 on the other 4 holes. The probability that they didn't get a hole in 1 on the other 4 holes is 2/3 to the 4th, and that they got the hole in 1 on the first hole is 1/3, and so the probability of that whole sequence is 2/3 to the 4th times 1/3. And then, as you mentioned, there are 5 different spots that they could have gotten that 1 hole in 1. And then, couldn't you have used Bernoulli trials? So actually, that's what we did. If you can reframe this as the following experiment. You have 5 Bernoulli trials. You have 5 Bernoulli. If you're familiar with the Bernoulli trials, then you'll understand. So you have 5 Bernoulli trials. So this is the value of n, and then the value of p is 1/3. So the outcome of this experiment is a binomial random variable with n equal to 5 and p equal to 1/3. So if you just want to think about it more algorithmically, you can just say that the outcome, or you just let x equal to the number of holes in 1, and then x is a binomial random variable with n equal to 5 trials and p equal to 1/3, and then you can go to the binomial table to look up the probabilities if you wanted to think about it like that. But we did the same thing. We just worked it out a little bit more carefully. But if you wanted to think about it more algorithmically, and just if you recognize that it's a binomial random variable, then you can just figure it out much quicker. But in general, you want to be in this class, you probably don't have a binomial probability table, so you need to you're better off just kind of carefully thinking it through. So this is kind of a useful strategy as well. All right, so but the next problem, part B, is the same. I mean, it says, what is the probability that in 5 holes the golfer gets a par at least twice? This is the same problem, except it's par instead of a hole in 1. So whereas if you're thinking about it from the point of view of just Bernoulli trials, your value of p, instead of p being 1/3, it says they're getting a par. So the value of p is a 1/6 now. and everything repeats. We could have used the exact same strategy that we used for part A. There's no, the strategy is the same. Okay. So here's the last part is a little different. It says, what is the probability that in 3 holes, the golfer gets a par more times than they get a hole in 1? I'm gonna get rid of this, the stuff here. Okay, so the golfer gets a par more times than they get a hole in 1. So let's let the event A represent just that they get a par more times than they get a hole in 1. So what did you get? It seems that some of you may have had the opportunity to look at this already, which is great. Does anyone like to share their strategy? All right. So we're gonna try to disjointize this event into a collection of disjoint events for which we know how to compute the probability of each, and then we're just going to sum them together. So they could get a par 0 times. So they could get a par either 0, 1, 2, or 3 times. So that's we're going to divide our event of interest into those 3 different cases and then compute the probabilities in each of those cases. So if they got a par 0 times, then could they have gotten more pars than holes in 1? Yeah, so yeah, that's right. No, they could not have. So we don't have to worry about that. The next one is they got a par 1 time. So in this case, how many ways can they get more pars than holes in 1? So there's only one way this can happen now, and that would be the case that, yes, that's right, William, that they got no holes in 1. So we have to compute the probability of that event. So they could get 0 holes in 1. Okay, so we need to compute the probability that they rolled 1 par, or they got 1 par and no holes in 1. So, well, there are, it could, that we have to select a hole for them to get their par in. And we have to, then if there are no holes in 1 and there's 1 par, they had to get the anything else category in the other 2 holes. So there are 3 ways to select the hole where they got the par. And then we know in any of those 3 ways, they got the 1 par, so that accounts for the 1/6. And then in the other 2 holes, they got anything else, which happens with probability 1/2. So the probability that they got 1 par and no holes in 1 is this quantity. Right. Okay, so then we just have to keep going, because Ultimately, we want to compute the number of um, the probability that the golfer gets a par more than they get a hole in one. So we just did the cases where they got 0 pars and where they got 1 par. So now what about if they get 2 pars? Same strategy here. So just write these out. If they got 2 pars, we have to be slightly more careful, but there are now a couple of different ways this could happen. So it could be that there are 0 holes in one. If there are 0 holes in one and there are 2 pars, there we have to select the 2 slots where they got the par, which is 3, choose 2. And then you have now 1/6 squared to indicate the probability of getting par in those 2 holes. And then we know they got no holes in one. So in the other hole, they got the anything else category. So this would be 1/2. And then they could have gotten 1 hole in one as well. That would also be okay. They would still get more pars than holes in one. So in the 1 hole in one category, so now we have two pars and 1 hole in one. So same idea here. You have to select the two holes where they're going to get par. So that's 3, choose 2. And then for each one of those possibilities, sorry, my drawing messed up. So you have your 1/6 squared because they got 2 pars. And then you have the other hole, they got a hole in one. So that has probability 1/3 of occurring. Okay. And the 3, choose 2 is just equal to 3 here. Okay. All right. And then they could have, there's one more thing to deal with here. They could have gotten 3 pars. And in that case, if that happened, they definitely got more pars than holes in one. So, and actually, when you're computing if they got 2 pars, you don't have to. Well, you have to compute the probability that they got 2 pars, but you don't. Any way you can compute that is fine. We split it up into 2 cases where there was 0 holes in one and there was 1 hole in one. But any way you compute that they got 2 pars would be sufficient, because whenever they get 2 pars, they definitely got more pars than holes in one because there's only 3 holes. The way we did it, we added these probabilities up. So we disjointize getting 2 pars into getting 2 pars and 0 holes in one, or getting 2 pars and 1 hole in one. That was one way to compute that probability. So for 3 pars, well, there's only 3 holes, so it's just going to be 1/6 cubed. So then you would just add up all of these probabilities, and that would be the solution. Are there any questions about this problem? James, is there anything that they should know that I did not communicate?
No, I think that kind of covers most of these problems that deal with Bernoulli trials.
Okay. All right. Let's do another problem. Do you guys have one in mind that you would like to see? If you just type it in the chat, we could try to do that one. Um, 3A. Let's see that problem. Oh, I have the continuous scroll. Here we go. Oh yeah. Okay. All right. So Miles says 3A and then Daxton says 7. Um, we'll start with 3A. And if there's time, maybe we can look at 7. Okay. So this is a kind of a tough one. It says you're playing blackjack and want to know the probability of getting dealt certain cards. In blackjack, 2 cards are drawn from a deck. The first card is dealt to you face down, and the second is dealt face up. Using the product rule, find the probability that the bottom card is an ace or a king and the top card is red. That's the hard part, I think, of this problem, the part A. I think B and C, if you know how to do A, you'll definitely be able to do B and C. So, it can be helpful when you're doing probability problems to have some notation in mind, to just to make to know what you're trying to compute the probability of. So let's have some notation. Let's let E1 be the event that the bottom card, I'll just call it card 1. Card 1 is an ace or a king. Or a king. Okay. And let's let the event E2 be the event that the second card, card 2, is red. Okay. So we want to compute the probability of E1 and E2. These are really two. These consist of sets of events, and yes, these are both events in our sample space. They're really sets, and this is an intersection. So we want to compute E1 intersection E2. So now, as far as setup goes, it might be, well, it's easiest to motivate the next step by at least writing out how we would approach this if we, okay, actually, what's up, you?
Oh, I have a thinking about this question. I'm thinking that it's ace or king that double the possibility of it, and then times the possibility of top card. So I think it's gonna be finding like C from it's gonna. Are there like 4 aces and 4 kings?
Yes, there are 4 aces and 4 kings in the deck.
Okay, so that will that be finding the possibility of taking 1 ace, finding the possibility of finding an ace and then times 2 because they're same numbers of kings, and then times the possibility of picking a top card is red.
Okay, so I'm just writing out what you have here. So you have probability of drawing an ace or a king, or just you have 2 times the probability of drawing an ace.
Yeah, because I think the probability of getting an ace and getting a king is the same.
Yes, that on your first draw of a card, you are just as likely to get an ace as a king. That is correct. Yeah. And then I'm just going to write down. I'm not saying that this is right. We're going to go through kind of a more systematic way to do it, but at the end we can come back and compare the solutions. So I want to get down the other part of it. So what's the last part?
Oh, and then time the possibility of the top card is red.
Okay, top card is red. Oh, okay. So this is a good start. The thing is that these are not independent events. So it's hard to know what the probability of the top card, what the probability that the top card is going to be red if we don't know what the color of the first card was. So somehow we have to account for that a little bit. So that's actually good motivation for what we're about to do. Yes, we're going to split it into cases. That's exactly right. The event E2 is just this event, and we're just going to split it into cases. So first, before we do that, we're going to split E1 up into cases. We're going to note that in E1, you either draw an ace or you draw a king. So we're just going to have E1A. That's going to be the event that the first card drawn is an ace, and E1B. That's going to be the event that the first card drawn is a king. We know that the event E1 is equal to the union of E1A union union E1B. Okay, if they drew a ace or a king, either E1A or E1B had to happen. So then we can rewrite this event E1 in terms of E1A union E1B intersected with E2. Then we're going to distribute. So we're just, yeah, we're going to use the distributive law for sets. This is just E1A intersected with E2. And then we have the union with E1 B intersected with E2. Okay, all right. So now we're going to note that these are disjoint events. If E1B happened, they got a king on their second card. So they didn't get an ace. So definitely E1A didn't happen. So using the disjointness, we can represent this as the probability of E1A intersection E2 plus the probability of E1B intersection E2. And finally, we're going to use our formula for the joint probability. We're going to represent, we're going to represent joint probabilities in terms of conditional probabilities. So we can rewrite these joint probabilities. Let's just recall that if you have two events, A and B, and you take their intersection, the probability of A intersection B is the probability of A given B times the probability of B. So that's all we're going to use. So the first term is going to be the probability of E1A given E2 times the probability of E2. Yeah, and then the other one is the same idea. So this was really all just notation, but we've split up. All we really did was split up the event, the first event, into its two possibilities. It'll be a little bit easier to reason about E1A given E2 as opposed to E1 given E2, because there are two distinct outcomes that can happen in E1. So that's why we split it up. So just writing this out, here's E1B given E2 times the probability of E2. Okay, so all right. Okay, so now we can, oh no. Okay, I conditioned on the wrong event here. So this is a common issue. I think I did something wrong here.
Yeah, this is technically correct. You can
Yeah, it is.
condition on either, but it'll be a lot harder
Yeah.
to know the probability of E2 compared to the probability of E1.
Yeah, so we have to fix this. We need to condition on the event E1, not on the event E2. So, oh boy, let's try to fix it.
Yeah, so it just in the last equation that you wrote. As long as you swap every 1 with a 2 and every 2 with a 1, it'll be right.
Okay. Well, I mean, I know I want a condition on E1 here. So, I mean, I'd like to condition on E1, but now my notation's all screwed up. So what exactly is what is E1A supposed to be then? That should be,
I have a question.
what's up?
And so those two, is that two cases? One of them is if the first draw is a red card, that will reduce the possibility of getting a red card second time. And then if the first draw is not a red card, the possibility will still be like there will still be
Yeah,
third.
yeah, that's
13.
right. That's right, Yu. Okay, so I see what the problem is. Yeah, I should have conditioned. We want to condition on the events E1A and E1B, and then compute the probability of E2. That is a problem. We can fix it though. It's very easy to fix. So I'm just going to erase this here. So again, my issue here, and this is a common issue when you're dealing with conditional probability, we need to condition on the event that is hard to compute its marginal probability. Otherwise, we didn't really help ourselves. So we're going to take this first event and condition on E1A and not on E2. So this is probability of E2 given E1A times the probability of E1A. Okay. And then the second event is computed in the say it's probability of E2 given given E1B times the probability of E1B. Okay. So so we're almost there. Now we just have to compute the probability of E2 given E1A. Let's start with that. So probability of E2 given E1A. Okay, so E1A, recall, is the event that the first card selected is an ace. So how many ways are there to do that? There are 4 over 52 ways to do that. So that's the probability of E1A. So the probability of E1A is 4 over 52. That's the probability of E1A. So let me just erase this here. Okay, so the probability of E1A is 4 over 52. Now we have to compute, that's this. That's this. Then we have to compute the probability of E2 given E1A. Okay, so this one, we have our denominator, which is the size of our sample space, and then we're going to have our numerator. So I'm just kind of making some division there. Okay, so E1A. There are, the way to think about this is that there are 4 choices for that ace. And for each one, we're then going to make a choice from that deck of 51 remaining cards. But there are 4 different possible decks of 51 cards that would be remaining. So, and this is the difference of computing the sample space in a marginal probability problem versus a conditional probability problem. We now have 4 possible decks of 51 cards to choose from instead of just 1. So we have 4 times 51. So again, the idea here is that there are 4 possible decks that we could have resulting from choosing a particular ace, because there are 4 different aces, and each of those decks, when we remove the ace, has a total of 51 options left. So that's how we ended up with 4 times 51 in the denominator. And then in the numerator, we want to compute the probability of the event E2, that the card is red. And this is exactly now what Yu was talking about, that there are a total of 2 black aces. So if the card that was, if the ace that we chose was a red ace, then, and that can happen in 2 different ways. And then in order to choose a red card, there would only be 25 remaining red cards if we had chosen a red ace. So that's one way in which we can end up getting a red card. The other way that we can end up getting a red card is if the ace that we had chosen was black. There are 2 ways it can be black. And then if we had chosen a black ace, there are still 26 red cards remaining in the deck. So there are 2 times 26 ways where we could have chosen a black ace and then a red card. So this is the probability of E2 given E sub A 1A. Okay, so if you multiply these 2 things together, then that gives us this. And then the other probability is computed in an analogous way. So the moral of the story on this problem is we had this event E1, which is that card 1 is an ace or a king, and we split it up into 2 events, which made it simpler to compute these conditional probabilities. You could also try just trying to compute the probability of E2 given E1 times the probability of E1. So the probability, yes, that's right, yeah. Yes, it's just a king instead of an ace. Yeah, you could also have tried to do, you could also not split it up like this and just try to leave E1 as it is and then condition on E2. And then condition on E1 and try to compute the probability of E1 given E2, but it would have been a little bit more complicated. So yeah, so that's the approach on part A. Yeah, so this one's kind of like a conditional probability problem. Are there any questions about this problem or anything else? Daxton mentioned number 7. I know we're out of time, but maybe I can give an idea of what to do on 7. I'm not sure. If you have to go, you should just go. But let's see, I might be able to give a hint on 7. Oh, okay. So the hint, since we don't have time, the hint is so the expected number of seniors, we're trying to compute how many seniors are in the club, and the expected number of seniors is 2. Okay, so on this one, have some variable. The hint is, and this is just a starting hint, you'll have to do more thinking. Have some variable X that represents the number of seniors in the club. Seniors in the club. And then using all the, you can ignore this little line for a moment. And the first thing you should do is compute the expected value of X, given that there are 10 juniors in the club and X seniors in the club, and then equate that to 2. That's what this line gives you, and then solve for X. Expected value. Yeah, so X, my notation is, sorry, my notation isn't good. My notation, I'm overusing things. X, so yeah, you can let X be the number of seniors in the club. There are 10 juniors in the club. And then, you need a, so one second here. I'm just going to erase this. You need, X is the number of seniors in the club. Yes, you can write X, that's a variable representing the number of seniors in the club. Then you need a random variable. So X is not a random variable. It's just the number of seniors in the club, and it's just an unknown. But we do have a random variable. Let's call that P, and that's the number of seniors in the committee. Number of seniors in the committee. And then what you should do is compute the expected value of P as if there are X seniors in the club where X is unknown, and that there are 10 juniors in the club. Try to compute the expected value of P and then set it equal to 2 and solve. This is going to be a function of X. This will be some unknown function of X. So you're going to have the expected value of P is going to be a function of X. X is the unknown number of seniors in the club. You're just going to find the expected value of P. It's a function of X. It'll be equal to 2. And then you'll solve for X. That's the setup for that problem. So it's 3:43, so that's it for today. Have a great day, and I'll stick around for just a minute or two in case anyone has any last questions. Also, James, do you have office hours at 2 p.m. today?
Yep, 2 to 4.
Sorry, I still just had kind of a quick question on 3A that I wasn't super sure about. If you've got a couple minutes. If not, that's totally okay.
Oh, no, I have time. I just closed the whiteboard. How do I get that back? I think I might be able to get it back. Oh, no. Okay, well, that's all right. What's your question?
So actually, yeah, it doesn't really involve any of the work that we actually did on screen. I was just wondering if there was a separate way potentially to do it, because I have it kind of set up initially as the aces and kings are 8 over 52, right? And then you can multiply that by 26 over 44 for the case that all 8 of those cards weren't red, I guess. And then could you also calculate the probabilities of each additional red card in the aces and kings after that, if that makes sense?
Okay, wait, the 26 over 44 is the number of red cards that would, what is 26 over 44?
So 26 cards in the deck that are red, if the original 8 aces and kings mixed together were all black. And then could you potentially calculate the other cases? Because that's just kind of the first case, right?
Well, the issue here is that and I'm not an expert on cards. You know, I don't play cards, but apparently there are 4 red cards in the deck. There are 2 for every suit. Well, I don't know what it's called. There are 2 red kings and 2 red. There are 2 red kings and 2 black kings in any deck, and there are 2 red aces and 2 black aces in any deck. So we don't have to enumerate possibilities about what colors the aces and kings might be. We happen to know that there are that there are 2 aces, 2 red aces, 2 black aces, and 2 red kings and 2 black kings.
Gotcha. Okay. Okay. So that's 4 red cards total of the kings and aces.
Yeah.
Okay. And then could you potentially, so if that's only 4, let's see. So that would be 26 over 48 then, potentially?
If you were to remove those 4 red cards from the deck, you would have 26. You're removing the 4 black.
Or yeah.
You're removing the 4 black
Yeah.
aces and kings from the deck.
Mm-hmm.
Okay.
I guess I'm trying to just like figure out like an alternate way to kind of look at this, I guess. Just because I was kind of getting confused in like the general like intersections and unions of the different events.
I see. Well, the issue is that you can't, you're only drawing 2 cards. So you're not going to be able to remove all of the cards of one color in that first selection. Or you're only removing one of the aces and kings. So you're not going to, yeah. So I'm not sure that this will work. I mean, this, unfortunately.
Gotcha. Okay. Yeah. Just wanted to make sure.
Yeah.
All right. Well, thank you very much. I'll keep working with it and see what I can do.
Yeah, and ask on Piazza if you have questions, or James, he's definitely much better at explaining things than I am. So at 2 p.m. he has office hours as well. So.
Awesome. Yeah, thank you both. I seriously appreciate it.
Yeah, no problem. Yeah, definitely. Yeah, I don't know if there's too many different ways to solve this one, just because the 2 events are dependent upon each other. So at some point you'll have to use the general product rule using the conditional probability.
Gotcha.
And there won't be a way to get around that because the events are dependent. So you just have to be careful about that. The one thing I would also caution, if you do find an alternative way, to make sure you didn't consider the events to be independent, because you'll end up, for this particular problem, if you calculate it assuming they're independent, you'll get the same answer as if you assumed that they were dependent. But if you calculate it with the formula using independent, that's wrong. You just happen to get lucky.
Gotcha. Okay. Okay. That makes a lot of sense, actually. Yeah.
In general, that will not necessarily be the case.
Okay. Awesome. Well, yeah, thank you so much. I appreciate that.
Mm-hmm.
All right. We'll see you guys next Friday, I guess.
Have a good one.
Thank you, you guys too.